Science on Surfaces. A bigger perspective on the small.
Welcome to this podcast, Science on Surfaces, a bigger perspective on the small. Here we zoom in on science that impacts our everyday lives, and today we will talk about nanotechnology, opportunities and safety challenges. My name is Malin Edvardsson, and here with me in the studio I have Professor Bengt Kasemo. You are Professor of Physics at Chalmers University of Technology. You are a member of the Royal Swedish Academy of Sciences and a member of the Royal Swedish Academy of Engineering Sciences. Welcome.
Thank you.
So you have long experience in surface science, and you also work on nano-safety and nanotoxicology. So the nano prefix, it's an SI prefix, meaning 10 to the minus 9. So a nanometer is a billionth of a meter. So just to put that into perspective and relate it to well-known objects, for example, the diameter of a strand of hair is typically 50 to 100 micrometers, which would then be 50,000 to 100,000 nanometers. And a water molecule is about 0.3 nanometers. So the nanoscale is in between the atomic scale and the microscale, you can say. So it's very small. So what is the nanotechnology or nanoscience?
Yes, nanoscience and nanotechnology in a broad sense deals with matter and constructions of matter in this size range that we were talking about. You were mentioning. So water molecule, 0.3 nanometer is a little small to be nanotechnology, but if we go up 3 times in size to 1 nanometer, we could have a few hundred water molecules or other molecules in some construct, a few hundred, about 1 nanometer. And then if we go up 2 orders of magnitude in size, up to 100, the volume actually goes up 10 to the 6 times, a million times. So we're talking there about millions and tens of millions of molecules. And we are still in a size range of, say, 100 nanometer. And to put that into perspective, it's about where an optical microscope stops to see things. So in this size range, we can build things with a few tens of atoms, molecules, or we can build things with millions of atoms, molecules that have special functional properties. And functional is a key word for nanotechnology. So when we scale down from macroscopic to micrometer to nanometer, at some point matter very often changes its properties in a dramatic way. And this change of properties is of course a challenge for all researchers who are just interested in finding out what happens, what can you do, what can you construct. But it's also of extreme importance to make new functional units in electronics, in material science and so on. And there are different people, different researchers or engineers want to exploit these new properties.
So why, how did this start? When did it start and why?
I think you get different answers from different researchers or technologists, but my picture on what started nanotechnology is actually microelectronics. Microelectronics was the revolution in electronics that happened when we made a transition from radio tubes, which were abundant up to 1950s, and the discovery at Bell Telephone Laboratory that one could build a unit that resembled the functional properties of radiotubes by making a so-called transistor, which was a solid-state device. And this happened in Bell Labs 1947, I think. It got the Nobel Prize a few years later, but really started to revolutionize the building of circuits at the end of the 1950s and through the 1960s. And then started a development where every transistor and every other component, diodes and so on, shrunk for every year.
For a specific reason.
For a specific reason. And the reason was, of course, that you get more functional units in a microcircuit, the more transistors you had. So by close packing, you could gain in performance, you could also gain in speed, and you could gain in cost. And this started really on the macro scale in, say, around 1960. But then, as the components shrunk and shrunk and shrunk, we take a step over about 40 years ahead, we find that the smallest part of integrated circuits, a transistor, actually passed the size of 100 nanometer.
Okay.
And then we, or they, found that there were some limits they were starting to run into, how to make things so small. So the perspective of microelectronics shrinking below 100 nanometer put a lot of effort and attention to making things smaller and smaller and smaller. And making things smaller and smaller and smaller required two things, or many things, but two special things. One is a production unit, production instruments that could make things small, using, for example, photolithography and later on electron beam lithography. So making things small was very important, but also seeing things. Analytical instruments that could see things were also very important, like electron microscopes and scanning electron microscopes, since optical microscopes couldn't see the smallest components.
Right.
And this put an enormous drive on technological development of producing and analyzing, and this spilled over from microelectronics into essentially every area of technology, but also into science, pure science, to make things small. In my view, that is was the strongest driving force. But there was another parallel development in chemistry, and that was to make things, functional molecules that were larger than what we normally call molecules, nano objects, nanoparticles. To make these nanoparticles from the very few, around 1 nanometer in size, to many, up to 100 nanometer in size. And that was a parallel development that complemented the one from microelectronics.
Okay. So there were some parallel tracks. There is a drive within the microelectronics area to go smaller and smaller. And to do that, you need to be able to manufacture at this smaller dimensions and also to measure.
Yeah.
And then this spills over. But why did it spill over? I mean, so the benefits of these small objects in other areas, like you mentioned nanoparticles, for example. What is the benefit of the small size?
Well, in one way you could answer that one did not know what the benefit was. It was more a curiosity-driven search for what are the properties of this material if we construct it at the size of 10 nanometer. And very often there was some evidence, even for the bigger particles, say 100 or 200 nanometers, some evidence that properties started to change.
And then we're talking about what kind of properties?
We could talk about electrical properties, because when electrons are moving through objects that are very small, sufficiently small, you get quantum effects because of the small size,
Mhm.
and things like Ohm's law, and
Mhm.
you start to see deviations from things like Ohm's law. You can see, for example, that the current voltage relationship is like a staircase. It's not a straight line.
Okay.
Current versus V is
Mhm.
a straight line. That's Ohm's law.
Mhm.
But for sufficiently small units, it can be like a staircase.
Okay.
And it's related to something called Coulomb blockades, that electrons feel each other in very small objects and repel each other and change. So sometimes you can get one electron at a time, and later on 2 electrons at a time at a higher voltage, and that creates a staircase, for example.
Okay. So there are phenomena that becomes visible,
Right.
that are always there, I guess, but they become visible at this
They
scale.
become visible. They become, so to speak, not buried in other behaviors, but they become purified. And this search for new behavior or possible new behavior was curiosity driven, but as discoveries were made, they could also be exploited into practical things.
Mhm.
Another area is simple inverted commas material science, that if you build things with combined units like fibers and particles and so on, and you align them, you can get materials with extreme strength.
Okay.
And you can also get things with materials with very anisotropic mechanical properties. They can be soft in one direction and very hard in another direction, and so on.
Mhm. And then you also have you can have different thermal properties and different optical properties.
Right.
I guess.
Optical properties, of course, since you're approaching length scale, which is below the wavelength of light. So light behaves in new ways. Excitation, the way light excites electrons, happens in a different way, and this gives rise to color effects that are surprising.
So the wavelength of visible light is 400 to 700 nanometers,
Right.
something.
That's right.
Which is a bit then above.
Above what we normally define as the upper limit of
Yeah.
nanoscience, which is 100 nanometer.
Yeah.
But there is a boundary. Actually, it's appropriate to say that the actual limit, the upper limit of nanotechnology is different for different properties.
Okay.
So sometimes the nano size properties may disappear into macro scale properties already at 100 nanometer.
Okay.
And sometimes they don't disappear until, say, 300, 400, 500. So the upper limit is a little, it's a gray zone.
Okay. So I know that nanotechnology or nano-sized objects are used in many areas today. For example, sunscreen, food, energy. Could you say something about this, like where we can encounter nanotechnology in our everyday life, except in electronics?
So if we take go back to the integrated circuits, the microelectronics, these are very, very advanced nanotechnology objects. The smallest transistors now maybe, I don't remember exactly, but I think around 15 to 20 nanometers, the smallest. So they are, since almost 20 years, have been in the nanotechnology regime. But here all the objects are stuck, manufactured on a silicon surface. They are not free particles. But in other areas, one works with free particles, like you mentioned, the sunscreens. And there it's titanium oxide particles that reflect light in a special way. And so the functional properties there is a combination of the optical properties, but also the properties to be that this sunscreen is possible to spread on the skin to get the effect. So they are very, very often very combined properties, different combined properties to make the ultimate functional product. This is exploited in very serious applications, but there are also less serious. If you look in products on the market that use nano as a prefix, you can find almost 2,000 or something like that.
Oh.
And they're like anti-graffiti. There are even condoms that are given the prefix nano.
Okay.
And these are, I would say, less serious products. But so there is a whole scale from very advanced serious to much less. One special area is in medicine and medical technology. For example, the Nobel Prize, was it last year or... No, it wasn't last year, it was a couple of years ago, was given for nanorobots.
Okay.
Small molecules that could move and very rudimentary robots, but still opening an area where one could make small objects that are small enough to penetrate into human cells, and we could anticipate for the future carrying drugs with them. And also having sensors on the surface that can sense what type of cell am I approaching. So a nanorobot that is both a sensor to find the right cells, and here is a cell I should go into.
Okay, that's...
And then it can go into, is made to go into, and then it's made also to release its cargo of some drug or some signal chemistry.
So this is an advanced version of nanomedicine, I guess.
It's advanced, and nanomedicine in the area of drugs is actually composed of many different components. It could be a drug that is carried by the nano object, but it could also be a nano object that amplifies pictures from analytical instruments like X-rays or NMR, magnetic resonance imaging. So, for example, magnetic nanoparticles are tried. Magnetic nanoparticles that are made to attach to special cells are tried to improve the pictures in magnetic resonance imaging, MRI.
And this exists? Or
this exists already. And also target-seeking drugs. Target-seeking in the sense that they go only into one type of cell. Or try to make it possible to increase the deposition of, say, cancer cell drugs into the right cells, into the cells one want to reach. Because if they don't go into the normal healthy cells, you can increase the concentration.
And this also exists?
This also exists. There exist a few drugs. There are many which are in clinical trials, and even many more on the research level.
Yeah, that's interesting. So I'm thinking for the nano, you have nanomedicine and you had the sunscreen. I know also that you use nanotechnology for antibacterial properties, for example, in sports clothes, where you have silver nanoparticles, right? Or maybe you use some other particles for that?
The silver particles are the most common.
So how does that work?
Basically, the silver is antibacterials, and by supplying them, in the form of nanoparticles, you get a large spread, you get a good distribution in order to obtain this antibacterial effect.
Mm-hmm.
It's an area which is very debated, and I think the attitude today is that it's maybe not a very good idea, because these antibacterial silver particles, when you run your stockings or socks in the laundry machine, come out into the environment, so they have a positive effect as antibacterial agents, but they have a negative effect as an environmental polluter.
Right.
And there are many examples here where you can see you can get an advantageous effect, but then you also have to balance that with the disadvantageous effects that might occur somewhere else or later.
Yeah, exactly. And that brings me to the question of the drawbacks, because we've talked about the benefits and the benefits of the size and the dimension, where you have all these different properties that you can take advantage of. But then you mentioned now some drawbacks. So what are then the drawbacks of the size or the dimension?
Well, the most honest and straightforward answer to that question, which relates to what is called nano-safety or nano-risk, is that we basically don't know, or more correctly, we know very little.
Okay.
Think about the area of nanodrugs. If we compare nanodrugs with normal drugs, we know that a normal drug has maybe 10, 15, 20 years of research and preclinical trials, clinical trials, and so on, to investigate the positive effects versus the negative effects. And in order to evaluate how a particular nanoparticle will affect the body, not only in the positive sense, but in the negative sense, you need similar efforts as with drugs. You need a sequence of screening steps, which for drugs starts with basically synthesizing the drug on a computer and then making many versions, maybe thousands or 100,000s of versions of that chemical, and do what is called rapid screening or fast screening in cell experiments and so on. And maybe you eliminate 99% of the candidates. And then you go further to animal experiments. You eliminate further, and maybe someone survives. And survives and maintains the positive effects, so that you actually can go into preclinical trials and even clinical trials. So it's an enormous costly process to verify that the benefits are higher than the drawbacks.
And this is years we're talking about.
Many years. And for nanoparticles, if you're going to evaluate a particular type of nanoparticle, say a titanium oxide nanoparticle or a composite nanoparticle, for its possible safety and toxicity effects, you have to do a similar screening as for drugs, but you don't have the positive effect there. You just want to
So you don't have the motivation.
You don't have the same motivation to do it. It's a very costly thing to ascertain. So this, if I should call it fear or worry that nanoparticles may have negative effects, is slowing down the development very much. Now there are different ways you can remedy this. You can say, if I can't evaluate what the risk is, maybe I can eliminate the exposure risk, because if you're not exposed to nanoparticles, there's still no risk. And so in the use of nanoparticles and nanoconstructs, nanomaterials and so on, a very important part is to actually make sure that the functional unit doesn't produce particles that are exposed to humans or even to animals or ecosystems.
Not released into...
Right. So you can try to evaluate the risks, but you can also try to evaluate the exposures. Eliminate the exposures. Sorry.
So there is a risk of these nano-sized objects, potential risk. We are not sure, and they can be made, of course, synthetically, like we've discussed. Intentionally, you manufacture these, and maybe then you can limit the release into the environment and exposure to people. But then we also have sort of unintentional production of these nano-sized objects. As byproducts in, for example, I don't know, maybe you can just...
road traffic?
Road traffic. I'm thinking about plastics that is released into the ocean and will break down to smaller units. So we are still exposed to these. So how can we handle that?
Well, first of all, you need to know what the exposure is and what the risk of the exposure is. And two concrete examples from the traffic system is particles from the asphalt, from the road material, or from the tires. So
just from wear, mechanical
wear of the rubber tires. So in both cases, particles are produced, that's known, and that has been measured. And they go into the sides of the roads and into the ecosystems. And the question is, what is the risk that they affect microorganisms and even higher organisms? So there are many studies of these unintentional exposures to see what is the risk and what can be tolerated. You mentioned plastics. We have followed in the last, I think, 5 to 10 years that the attention to plastic garbage in the sea has been increasing very much. The attention to this question has been increasing. And it started with plastic bags going into the stomachs of whales and so on. And then one finds that the plastics are worn down into smaller and smaller particles. And today we talk about microplastics. And it's only a matter of time before we start to talk about nanoplastics, because if a plastic bag is worn down to a micro particle, it will inevitably someday be a nanoparticle. And we have absolutely no idea what that type of nanoplastics will do to organisms in the seas.
Right.
So it's a good example of unintentional exposure, but we really don't know the answer.
But then I'm thinking, we are exposed to these particles. What can happen in the body?
What can happen is, I can say, what people who are worrying about those things, including myself, is that there may be effects of particles that are similar to what happened with asbestos. So with asbestos, the asbestos are particles that are much larger than nano size. They are, say, 10 micrometer. The worst ones are like 10 nanometer in length and about 1/40th in diameter. So the diameter is actually in the nano range. So what happened there was that lung cells that were engulfing asbestos particles, they could engulf very small ones with relatively little problems. But these 10 nanometer, that the particles that came inside the cell membrane could affect the cell so that it underwent some kind of a mutagenic change. And some of these changes were carcinogenic. And there were also cooperative effects between the particle itself and smoke from cigarette smoking and so on. So I mentioned this example on the macro scale from a nano point of view as an example of how one thinks about nanoparticles, that maybe similar effects can happen if cells that are very macrophages, for example, are very active in engulfing particles.
Yeah.
And the worry is, what does these particles do to the DNA coding into mitochondria, into the life processes? So this is a worry that something bad may happen, but one doesn't know.
Because now we are talking about similar size range. A cell is 10 micrometers.
Or
And so a nanoparticle would be a lot smaller.
Much smaller.
And could go into the cell and then...
Right, so it's a tiny object that goes into the cell and can affect many of those subcellular components that are of similar size as the nanoparticles.
Yeah, so what can we do to handle this risk? It sounds a bit complicated.
It is very complicated, but what we can do is, of course, to have a parallel development where we try, by research and development, try out what are the most interesting, advantageous properties that we can produce for electronics, for optics, for materials, for drugs, for medical analytical work. What are the most interesting applications that we can foresee? And then if we decide that we want to exploit those advantageous properties, we have to, in a parallel track, see, but what about the side effects? What about the possible negative effects? And to build a system not only for developing nanoparticles and their functionality, but also for screening their risks and negative effects. So in a way it's normal development of new products, but the problem is the enormous machinery, infrastructure that is needed to do the evaluation. It's very costly instruments, it's costly experiments and so on. So it has to slow down the development. I think as time goes by, we will learn that certain particles, certain features of particles, chemical or size-wise or shape-wise, are biologically active, as others are not. And finally, to go back to what I said in the beginning, that if you can build functional units that really don't expose the dangerous or the risky part, then you have done a good deal of the job.
So there is still a lot to be done in this area.
Most of it has to be done.
Most of it has to be done. So what are the most interesting opportunities that you see?
We have mentioned one of them, and that is in medicine. Both the analytical medicine, magnetic resonance imaging, other types of like X-ray imaging, analytical sampling by nanorobots and so on, and what we call nanodrugs. Drugs that are multifunctional in the sense that first they are passive in the body unless they find a particular type of cell that we want to reach, and when it reaches that cell it does something. It unloads some cargo or some drug, or it stimulates the cells and so on. I think that is an area which will develop tremendously.
So why is the nanoscale interesting for solar
cells?
Solar cells, yeah.
Well, nanoparticles and nanostructures can affect the solar cell in several ways. One is to optimize particles to collect wavelengths of a specific value. So a silicon solar cell is not optimal for all wavelengths. It's optimal for a narrow part. And by complementing, either making a new solar cell totally different or complementing a silicon solar cell by nanostructures, one can improve the spectral response, so one collects much more photons, much more solar light.
So a broader...
That's right, a broader spectral range where the solar cell is effective. But it could also affect so catching the light and creating an electron is just one first step in a solar cell. Then electrons should be producing a current or a voltage, which means that they need to move through the structures. And these motions through the structures can be also improved by nanostructures. And there are also other effects. So nanoparticles have a great promise as an amplifier, helper, enhancer of solar cells.
Okay. Any other areas that you see?
Well, we talked initially about medicine. What I forgot to mention there is one potentially very important area, and that is medical implants. Why should medical implants be better or worse with nanostructures? It is because it's very well known that nanostructures on the surface affect how cells behave. And behave means being good cells, creating good integration between the medical implant and the tissue and so on. And so basically nanostructures are explored to make possible the best possible interaction with the cells in the tissue where the implant is placed. Okay. So that's one area in medicine. Materials, generally nanomaterials, which could be macroscopic materials like tennis rackets or bike components and so on. Nanostructures give advantages in terms of weight, in terms of strength, in terms of anisotropy, that is, they can have one mechanical property in one direction and a totally different in another direction. But it could also be construction materials for industry in cars and so on. And by using nanostructures in materials that are macroscopic, one may also hope to solve this toxicity safety problem by encapsulating the material. So we don't need to evaluate, in the best case, we don't need to evaluate the risks, because we encapsulate and make exposure minimal or zero. One very big area which affects both energy and chemical industry is catalysis. And catalysis has been around as an industrial process for more than 100 years.
Okay.
Starting with ammonia production and catalysis is most catalysts, not every catalyst, but most catalysts are composed of some kind of a very porous structure with a very large surface area. Here comes surface science. And on this porous structure with very large surface area are placed very small particles, which are in the nano size range, say 10 to 50 nanometer. And they do the actual job of affecting molecules that should be catalyzed to produce new molecules. I mentioned ammonia synthesis. For example, ammonia synthesis is made by mixing nitrogen and hydrogen. And on an ion catalyst, nitrogen and hydrogen becomes ammonia.
Okay.
And ammonia is basic raw material for fertilizers. So it underlies a very big industry. The emission cleaning of diesel engines and of petrol engines, the cleaning of these exhausts are done by small noble metal particles, platinum, palladium, rhodium, sitting also on a porous area. And that's a very, very large area that can also affect energy, the energy area, because in order to enrich, to make fuels, for example, from biomass, to make really gasoline car fuels, you need to process it. And the normal way of processing raw materials into fine chemicals or more valuable chemicals is by catalysis.
Okay.
Well, the last area I would mention is sensors. So sensors can be made extremely small, extremely sensitive, and extremely multi-purpose type of sensors, that is, sense many different things, like in fingerprinting.
Okay, yeah.
Fingerprinting or, say fingerprinting. So by using nanoparticles-based sensors, one can make extremely small sensors that can be used in industrial processes, in industrial production, in surveillance of for toxic gases, or just to steer processes in a car. So nanosensors, I think, is one of the very potentially very important areas for the future. And again, with sensors, they can be made such that exposure from a toxic point of view or a safety point of view becomes small.
For humans or organisms.
For humans or organisms. You basically fix the sensing part into some other structure, like in microelectronics with nano transistors.
So we would then exploit the potential but then minimize the risk.
Right. So without having to do the evaluation of the risk, because exposure becomes zero.
So there are a lot of possibilities for nanotechnology within a range of areas, you could say.
There is no... Actually, when one talks about nanotechnology from a disciplinary point of view, the common understanding is that nanotechnology is not like a discipline. It's not like organic chemistry. It's usually referred to as an enabling technology, and it's enabling new technologies is essentially in any area of technology.
Yeah, that's clear from this discussion. So I think that's what we had for today. It was a great introduction to the topic of nanotechnology and related opportunities and safety challenges. So thank you for listening to this episode of Science and Services, a bigger perspective on the small, with me, Malin Edvardsson, and Professor Bengt Kasemo, Professor of Physics at Chalmers University of Technology. Thank you.